Assalamualaikum and good afternoon to all committee and participant of ICRMBEE 2023. Thank you to Associate Professor Dr. Siti Iqbal Saleh as a chairperson for today. My name is Nur Hidayah binti Zakaria and I am from Center of Study for Surveying Science and Geomatic, College of Built Environment, University Teknologi Mara, Shah Alam, Selangor, Malaysia. Today I would like to present my paper entitled Windstorm Hazarded Area Mapping Using Multi-Criteria Evaluation Technique of Fuzzy Logic Approach. This is my outline of presentation. We will go through one by one. First background, and then we go to problem statement, methodology, result and discussion, and lastly conclusion. First we go to background. Windstorm is classified as a tropical cyclone, thunderstorm, tornado, monsoon and gale by D. Henderson 2008. Windstorm event usually associated with precipitation, lightning, thunder and storm. Currently in Malaysia, wind-related disaster is not being given priority due to lack of expertise and awareness among the Malaysian. Study in Pulau Pinang on 2010 to 2013 shows the damages breakdown is about 47% damage targeted to the steel sheet roofing, 30% the truss system, and 30% the roof tile, and 20% other related component. According to prior study, the climatic factor, socio-economic factor, accessibility factor, and hydrological factor were the indicator that could trigger a windstorm occurrence. Fuzzy logic system assigned a specific output based the likelihood of the input condition. The use of fuzzy logic in short-term load forecasting has become commonplace with input variable including time, historical load data, and meteorological characteristics such as temperature, humidity, sunshine, light intensity, and so on. Next, we go to problem statement. The occurrence of more extreme weather events together with the increased social vulnerability of societies has been largely responsible for the increasing global incidence of natural disaster. The minimum of ground observation data has led to the necessity of exploring alternative solutions. Third, Malaysia currently does not have any complete database of windstorm occurrence and resulting damage. Fourth, the windstorm event impact has caused big impact to the urban metropolitan society, which is 80% damages of roof tile system in Peninsular Malaysia caused by windstorm event. And last, lack of information about windstorm event in Malaysia lead to this study. Next, we go to the methodology part. The study area for this study at Peninsular Malaysia. Peninsular Malaysia is part of Malaysia that lies on the Malay Peninsula and surrounding island. Malaysia is also known as Malaya, and its area is about 132,265 square kilometer, which is nearly 40% of the total area at the country. A bit info about wind at this country. It is a low latitude region and located very near to equator, hot and humid throughout the year, and the annual mean wind is between 7.2 to 9.54 meter per second throughout the year. For the data acquisition for this study, we are used 5 types of data, which is first, wind speed, temperature and relative humidity are using data from NECP NFL Operation Model Global Troposophic Analysis data from 2015 to 2018. Next, for DEM, to get the slope data, we use Landsat only. The date year is 2018. And for precipitation, we use data from Himawari 8 satellite data, date from 2015 and 2018. For data population, we retrieve from Department of Statistics Malaysia for recent data 2020. And for road and land use, the shapefile data we download from GeoFabric download server for data 20 and 20.
The figures show the framework for this study. 8 parameters was used to establish the windstorm hazard sensitivity map. For wind speed, temperature and relative humidity, the data was processed using WRF ARW software, while data precipitation and EM was processed into ArcGIS. For data population, road and land use, they were rasterized into raster layer. Then, all parameters were transformed into similar scale by using fuzzy membership. The fuzzy membership function constrained to be between 0 and 1. Since all the parameters have same scale, the parameters were tested by each other to see the relationship between parameters towards windstorm hazard sensitivity. The process using fuzzy overlay. Fuzzy overlay various methods have been defined to explore the relative relationship and quantify the interaction between parameters. There are 5 operators in fuzzy overlay, which is OR, AND, product, sum, and gamma. After all, gamma operator was selected by set the gamma equal to 0.9. The gamma operator was chosen because the gamma type is typically used to combine more basic data. When gamma is 1, the result is same as fuzzy sum. When it is 0, the result is same as fuzzy product. Value between 0 and 1 allow to combine evidence to produce result between the two extremes established by fuzzy AND or fuzzy OR. Then, the map of Winston hazard sensitivity for each parameter was established. The best combination of fuzzy was selected, and the best selection was selected based on the value near to 1. After that, the final output Winston hazard sensitivity map was established.
Next, we go to the result and discussion. As you can see in figure 2, windstorm hazard versus wind speed. Figure 2 shows the sensitivity of wind speed towards windstorm hazard. From the result, the higher sensitivity value is between 0.90 to 1.0 recorded in Perlis, which is 0.36% from a total area. Same goes to Titiwangsa Range and the West Coast Coastal Region Pahang, show the higher sensitivity value towards the windstorm hazard. As a result, its high altitude and proximity to the South China Sea, the location was very sensitive, mid-latitude wind between 30 to 60 degree latitude, flowing from west to east. They develop in equatorial high pressure zone, move towards the poles and employ with this motion to steer storm away from the tropic. Other sensitivities classes for another region was 0.0 to 0.09, 0.10 to 0.19, 0.20 to 0.39, and 0.40 to 0.89 account for 52.75%, 24.33%, 12.63%, and 9.92% of the total respectively. Next, windstorm hazard versus relative humidity. Figure 3 shows the sensitivity of humidity to windstorm hazard. The cumulative curve analysis species count identify 5 sensitivity classes. The greater the sensitivity value, 0.90 to 1, the greater the sensitivity of relative humidity to the windstorm hazard area and vice versa. High sensitivity value are located in the center of the map, high altitude region, which is comprised 2.59% of the map total area. The average relative humidity was between 86% and 75%. The high relative humidity suggests that the proportion of water vapor in the air is elevated. Thus, the surrounding became wet and frosty. Other sensitivity classes representing 50.850%, 30%, 36.83%, and 14.68%. Next, windstorm hazard versus precipitation. Figure 4 shows the precipitation of humidity to windstorm hazard. From the figure, the greater sensitivity value occupied 18.59% of the area, which is located at high altitude, which is at North, Perlis, East, Perak, Negeri Sembilan, and Malacca, and West, which is at Pahang, Kelantan, and Terengganu. High sensitivity implies a location that receives a lot of precipitation, which can lead a windstorm. As a result, the lower value suggests an area that receives less precipitation and has a low sensitivity to windstorm hazard. Other sensitivity classes was 6.17%, 1.46%, 10.46%, and 34.05%. Next, windstorm hazard versus temperature. Figure 5 shows the temperature sensitivity to windstorm hazard. The area occupied by the higher sensitivity value, 0.80 to 1, occupies 0.71% of Peninsula Malaysia. High sensitivity implies that the area has lowest temperature, forest and high altitude area, which can lead to windstorm. Thus, a smaller number suggests a high temperature urban and congested location with low susceptibility to windstorm hazard. For windstorm hazard versus population, Figure 6 shows the population sensitivity to windstorm hazard. The higher sensitivity map represents the dense population that occupy 2.61% of area. The more sensitivity are located at the urban area with high population. Thus, the lower value indicates the area low population area and cause low sensitivity to windstorm hazard event and vice versa. Other sensitivity classes represent 10.09%, 57.68%, 27.47%, and 6.15% respectively. Next, windstorm hazard versus road. Figure 7 show the road sensitivity to windstorm hazard. The higher sensitivity value, 0.81657 occupy 2.27% of area, represent the high sensitivity of road dense toward windstorm hazard area. The higher sensitivity located at highway of Peninsular Malaysia, while moderate sensitivity classes cover most of Peninsular Malaysia. Other sensitivity classes was 19.03%, 31.70%, 46.85% and 0.15% respectively. Next, for windstorm hazard versus slope, figure 8 shows the slope sensitivity to windstorm hazard. The high sensitivity value 0.989395 represent the high sensitivity of slope towards windstorm hazard area. The higher sensitivity value occupy 20.51% area which located at high area. High sensitivity indicates that the area has high slope and lead to windstorm hazard events. Thus, the lower value indicates the area that low altitude area and cause low sensitivity to windstorm hazard event. Other sensitivity classes represent 26.19%, 44.93%, 7.17% and 1.20% respectively. The final output for this study was windstorm hazard sensitivity map. After all the map from the fuzzy membership has been produced, windstorm event towards each parameter, the windstorm hazard sensitivity map was established. Figure 9 shows the windstorm hazard sensitivity map. The outcome of the various fuzzy operator were determined, and the algorithm sum and OR operation are yield precise result. Additionally, the combined fuzzy membership value for algebra product operator result in fuzzy membership value are uniformly distributed. Because it generates the most pertinent fuzzy membership value among the fuzzy operator, only the result gamma equal to 0.9 is displayed. Windstorm danger sensitivity map was produced using the fuzzy operator with gamma equal to 0.9. Area of this map having wind erosion sensitivity rating are categorized as very low, low, moderate, high and very high respectively. 10.65% study area has very high sensitivity towards windstorm hazard, which distributed at high area which is in Banjaran Titiwangsa, West Coast area Pahang and West Johor, and North area which is in Perlis. It is due to the presence of the high altitude area, lower temperature and higher precipitation distribution and high relative humidity percentage. In addition, some part of the surrounding region in Peninsular Malaysia were also identified as a windstorm hazard due to the dense of urban such as in the Johor Bahru. In the Klang Valley, with the area 7.20% of the study area has very low windstorm hazard and it's mainly located in the middle part. As a conclusion, when variables are complicated, fuzzy logic method have been found to be a very simple tool for determining the risk of windstorm in Peninsular Malaysia. In addressing the issue of remote sensing parameterization, the fuzzy logic approach to modeling windstorm hazard provide a valuable tool for differentiating the spatial heterogeneity of windstorm hazard across Peninsular Malaysia. The generated sensitivity map have clarified the disparate correlation between various input factors of windstorm. Gamma operator was used to combine the found sensitivity map, as the back success rate accuracy is 85.2%. Fuzzification has been considerable greater impact of the outcome than the way the merging different membership function. And last, the West Coast region has a high sensitivity to the risk of windstorm in high elevation area, which is in Banjaran Titiwangsa, Pahang and West Johor. Other dispersed locations were identified as having a most high and extremely high risk of windstorm. The windstorm sensitivity map is important for the construction of windstorm indices and future windstorm hazard reduction plan. That's all from me. Thank you.